Hello everyone, I am Dinesh Kumar Yadav, Assistant Professor in Department of Electronics and Communication Engineering at IIMT College of Engineering, Greater Noida. Today I am here to deliver a lecture on the cylindrical coordinate system. In the previous lecture, we worked upon the rectangular coordinate system or the Cartesian coordinate system. In that lecture, we saw that in a Cartesian coordinate system, we have three mutually perpendicular axes, and with the help of which we define the position or the location of any point in space. So another coordinate system is cylindrical coordinate system. So today we are going to see how it works. As you can see from this first diagram, which is on your screen, a cylindrical coordinate system is defined as making up of three different surfaces. First surface is first surface is a cylindrical body, as you can see in this diagram. It is the curved body which is being seen here, and this is the first surface, and the radial distance of this surface from the z-axis is represented as rho, as shown in the diagram. Second surface is the vertical plane. If you can see this, it is here, and this vertical plane is making an angle of phi, as shown in the diagram. So this is the second surface, and the third surface is the horizontal plane, which is shown on top of this figure. It is represented with the variable z, and it represents the height of point P. Here it is point P. This is point P. So the coordinates of this point P are rho, phi, and z. So let us discuss more about these three variables, that is the rho, phi, and z. Now rho is defined as the radius of this imaginary spherical body. Phi is the angle made or calculated by the xz plane. From xz plane it is measured, and that vertical shape which is shown to you, the angle between them is phi. The third variable here is z. The z variable is calculated or measured from xy plane. It represents the height of the point. So if point is P here, whose coordinates are rho, phi, and z, then z will represent the height. Rho will represent the radius measured from z-axis, and phi represents the angle made by this plane, this vertical plane on which P is there, measured from the xz plane. Okay. Now let us talk about the three unit vectors associated with this cylindrical coordinate system. In cylindrical coordinate system, we have three unit vectors: a rho, a phi, and az, as shown in the first figure with the red stylus. All the unit vectors are directed towards the outward normal direction of the increasing coordinates. For example, the unit vector a rho is directed towards the increasing coordinate rho. What is rho? Rho is the radius of the imaginary spherical body, cylindrical body. So if we increase the radius, it will be towards the outer direction, in this direction. So unit vector a rho is represented in this direction. Similarly, unit vector a phi, if we increase the phi, then this point P will move tangentially towards this direction, in this direction. So a phi is shown here. This was a rho, and this is a phi. Similarly, if we increase the height of this point P, then it will move upward in the upward direction. So this will be the direction of unit vector AZ. So all these three unit vectors are mutually perpendicular to each other, as was the case in rectangular coordinate system also. So because of this reason, the properties, all the properties of the dot product as well as the cross product are applicable here also. So let us see them one by one. The dot product of like unit vector terms will be 1, and the dot product of unlike unit vector terms like arrow dot a5, a5 dot az, az dot arrow, they will be 0. Similarly, the cross product of arrow a5, a5 cross az, az cross arrow. So this can be calculated with a very easy method which we discussed in the previous lecture also. If this is arrow, this is a5, and this is az, then if we move clockwise, then the cross product of arrow and a5 will be az. Cross product of a5 and az will be arrow, and cross product of az and arrow will be a5. Okay, so this is how we can make use of the dot product and the cross product. Now next is transformation. Transformation of coordinates. First part is transformation of coordinates, and in the second part we will learn the transformation of vectors. So now give attention to this diagram given below. This is the top view of the figure on the above. In this top view, I have incorporated the 6 unit vectors, both from the rectangular coordinate system as well as the cylindrical coordinate system. The unit vectors shown in black ink are from rectangular coordinate system. This is ax, unit vector ax, unit vector ay, and unit vector az is not visible to you because you are looking at its top view. So the unit vector az is coming towards you. So you can only see it as a dot. It is not visible to you. So you can imagine that it is coming towards you. And the unit vector arrow, it is here. Unit vector a5 is here. And unit vector az, obviously both the unit vectors az in rectangular coordinate system as well as cylindrical coordinate system are same. So az is again not visible to you. Okay. From the top view, it is clear that the angle phi is this, measured from xz plane, and the point P is this. So this plane, the angle between this plane and this axis, zx plane, is phi. So if this angle is phi, this angle is also phi. And because ax and ay are perpendicular to each other, so obviously this angle is 90 minus phi. Similarly, this angle will be phi. So, and one more thing, coming back to the top figure, if we draw perpendicular from point P towards the x-axis and y-axis, and obviously this angle is phi. So, and this is a right angle triangle. So what will be the value of this r, which is x? So x will be, and this is rho. So x will be rho cos phi. So this arm is rho cos phi, and this arm, the arm opposite to the internal angle phi, this arm which is parallel to y, this will be rho sin phi, and this arm is parallel to y. So I'm writing here rho sin phi. So that means x is rho cos phi and y is rho sin phi, and z is same in both the coordinate systems. So x is rho cos phi, y is rho sin phi, and z is same in both the coordinate systems. Okay. So using these three expressions, you can convert the coordinates given in terms of rho, phi, and z, that is in cylindrical coordinate system, into the coordinates in terms of x, y, and z, that is in rectangular coordinate system. What about the vice versa? So if we take x square plus y square, if we take x square and y square from the above three expressions, it will come out to be equal to rho square, or we can write it as rho equal to under root of x square plus y square. Similarly, if we divide y by x, it will be sin phi by cos phi equal to tan phi, or we can write it as phi equal to tan inverse of y by x. And as z is same in both the coordinate systems, so z is equal to z. So these three expressions are used to convert the coordinates given in one coordinate system into another. Next is transformation of vectors. We have learned how to convert coordinates from one coordinate system to another. Next is how to convert a vector. Let us suppose a vector is given to us in cylindrical coordinate system. Let a vector A is there. So in cylindrical coordinate system, we will write it as A rho, A rho, A phi, A phi, and AZ, AZ. This vector is in cylindrical coordinate system. It is given to us. And we are asked to find out its equivalent vector in cylindrical coordinate system, or we are asked to convert this vector or represent this vector into a cylindrical coordinate system. Now, in cylindrical coordinate system, what we require is vector A must be in this form: AX, AX, AY and AZ. Okay. Now, given vector is in cylindrical coordinate system and we require to convert this or transform this into rectangular coordinate system. Now, how will we do this? For converting this, we need to first know the value of AX, AY and AZ. Now, what are they? These are the components. So these components need to be first find out, then only we can write this vector in the rectangular coordinate system. So how to find out these components? Now these components can be calculated like this. AX will be vector A dot AX. What does it mean? That the component of a vector in a desired direction. What are we talking about? We are talking about component AX. Its desired direction is X. So the component of a vector in a desired direction can be calculated by taking the dot product of that vector and the unit vector in that direction. So which vector we have to convert? We have to convert this vector which is in cylindrical coordinate system. What is the desired component? Desired component is AX. What is the desired direction? Desired direction is given by the unit vector AX. So AX is equal to vector A and unit vector AX, the dot multiplication of vector A and unit vector AX. Similarly, AY is vector A and AY, unit vector AY, and AZ component is vector A and AZ. Okay. So let us try to find out this. AX will be A row, A5, AZ, dot product, unit vector AX. Similarly, AY will be like this. And AZ will be like this. Okay. Now from these three expressions, one thing is clear, that to find out the vector in the rectangular coordinate system, which is our aim, we need to first know what are the dot products between A row, A5, AZ with AX, AY, AZ, because these 9 terms we need to know, then only we can solve this. So for this, we have to refer this figure number 2, which is at the bottom of your screen. The first multiplication which we need to find out is, okay, let me first draw a tabular, draw this a tabular form so that will be easy for you. Okay. So we need to find out the dot product of A rho, A phi and AZ with AX, AY and AZ. So give focus to the figure given at the bottom of your screen. What is the angle between A rho and AX? If you look at this figure, this is AX, here it is, and this is A rho. Now the dot product of two vectors is simply the cosine of the angle between them and their magnitude, because we are talking about unit vectors, so their magnitude is unity. So what remains is that the dot product of two unit vectors is simply the cosine of the angle between them, and here the angle between them is phi. So ax dot a rho or a rho dot ax is simply cos of phi. I will write here. Similarly, a rho dot ay. This is a rho, this is a rho, and this is ay. And the angle between them is, as you can see, it is 90 minus phi. So cos of 90 minus phi. The dot product of a rho and ay is cos of 90 minus phi. It will be sin phi. Okay, next is a rho and az. A rho you can see, but az is not seen to you, as I told you earlier, because you are looking at its top view. So az is coming towards you. You can only see a point. But obviously the angle between a rho and az is 90 degree. So cos 90 is 0. So here it is 0. Next is a phi and ax. This is a phi and this is ax. So angle between a phi and ax, if you look closely, it is 90 plus phi. So cos of 90 plus phi is minus sin phi. Next is a phi and ay. A phi is this, ay is this. Angle between them is phi, so it is cos phi. Next is a phi and az. Again, the angle between a phi and az is 90 degree, so it is 0. Az and ax, obviously angle between them is 90 degrees, cos 90 is 0. Az and ay, it is again 0. Az and az, angle between them is 0, they are parallel, so cos 0 is 1. So now all the 9 products are all the 9 dot products between the unit vectors of different coordinate system are known to us. So we can easily find out the component ax, component ay and component az. Let me clear the page. Okay. So component ax was vector a dot a rho, and our dot products that came out were I'm referring to the diagram. So it was okay. A rho cos phi minus a phi sin phi. Similarly, ay was phi plus so if we put all these in the matrix form, it will be like this. A row, A phi, and AZ. So this particular matrix will help us to convert a vector given in cylindrical coordinate system to rectangular coordinate system. Similarly, if we want to convert a vector given in rectangular coordinate system to cylindrical coordinate system, this middle matrix will just make transpose of itself, and it will be written as cos phi minus sin phi 0, sin phi cos phi 0, 0, 0, 1, and in the third column matrix we have ax, ay, and az, the components of the rectangular coordinate system. So these two are the matrices for converting a given vector from cylindrical to rectangular or rectangular to cylindrical coordinate system. Now, one thing is also to be keep in mind that in a cylindrical coordinate system, the unit vectors a rho and a phi will change as point P moves in a certain direction. So while integrating or differentiating with respect to these variables, they should not be treated as constant, because a rho and a phi will always be changing their direction, while az will always remain in the upward direction, in the same direction, but a rho and a phi will always change their direction. So they should not be kept constant while differentiating or integrating with respect to phi. That's all for today. Thank you very much.